Hey guys, today we are going to discuss about integrals, right? Under integrals, we talk about Riemann integration, right? So first of all, we have to define a partition. Suppose we want to find the integral of f, the curve f, over this interval, over AB interval, right? So that means we want to find the area under this curve and bounded by this interval AB. So now what we do here, we split this whole interval AB into sub-intervals, or we partition this interval into small sub-intervals. Let's do that. This is our initial point. Let's denote this one x naught, x sub naught, right? And this is let's denote this is x sub 1, x sub 2, x sub 3. A general point, x sub say r minus 1, and this is x sub r and x sub r plus 1, and goes to, this is the last point, end point, x sub n. This is first sub-interval, second sub-interval, like that. This one is the r sub-interval, right? What we did, was we split this whole AB interval into sub-interval. So this partition, so this is a partition. Let's denote that. Oh, where's my pen? Let's denote this partition. Partition is P. The first point of this partition is x sub 0, which is A, x sub 0, x sub 1, x sub r, x sub r minus 1, r, and goes to, and what is the last point is this one, x sub n, which is same with x sub n, which is same with b. This is called a partition of this interval AB. This is a partition. You can find infinitely many partitions, right? This is a partition, right? Here, look at the definition of a partition, right? Suppose that A, B belongs to R, real numbers, A, B are real numbers such that A is smaller than B, right? So a partition P of this closed interval, very important, closed. So in this course we are talking about closed intervals and continuous function over that closed interval, right? So P is a partition of that closed interval AB, and a finite set. This is a finite set, not infinite set, right? Finite set. So it has finite number of points, right? With these conditions, right? So the starting point is with this A, x naught and x1, and this is a increasing sequence, finite sequence, up to this point, end point. This is the next, the other end point, So this set is called a partition. You can find infinitely many partitions. This is a partition, right? And this one is pretty obvious, right? If you split into sub-intervals like this, x0, x1, so x sub 1, x sub 2, this is another partition, and this is the nth partition, last one, x sub n minus 1, x sub n. This is the nth partition. So if you take the union of these partitions, you get that whole interval AB closed interval, right? If you take the union of these sub-intervals, you get this AB closed interval, right? It is pretty obvious. And let's talk about the length of each sub-interval. So length is defined by, so if you consider this sub-interval, let me zoom this picture a little bit. Alright, okay, so if you consider this sub-interval here, right, this one, so you can find the length of this one by subtracting x minus 1 from xi, x sub I minus 1 from xi. So you get the length of that interval, right? So as I said before, f is continuous. Very important on this closed interval. So if you have a continuous function on a closed interval, you can find maximum and minimum values, right? So that is called Min Theorem, right? So you can find, if you have a function which is continuous on a closed interval, then you can find maximum value of f and minimum value of f, right? So on each sub-interval, you know, this one also closed, and f is continuous on that one, then you can find max value and min value, right? You can find a max value. Let's denote that max value is m sub I. This is the max value of f on x on this interval here. On this interval, this is the max. Other one is, this one is the minimum value, m sub I of f. This is the maximum value of f over this interval, and simple m sub I denotes the minimum of let's go to this picture here, right? If you consider this wait a second. If you consider this, let's consider this picture here. If you consider this sub-interval x0, this one here, x0, x1 is in sub-interval, and this what is the maximum of f on that interval is this here, this value. Now if you I complete a rectangle like this, right? Then I can calculate the area of that rectangle, this rectangle, right? Which is, so let's say this is the maximum for so let's say the maximum value of f on this interval is m sub 1, right? So the so this height is m sub 1, times the width of this rectangle, which is x sub 1 minus x sub 0, right? So that gives you the area of this rectangle. I write in white, otherwise you can't see this. M, capital M, which denotes the maximum of f on this interval, times the width of that, the first sub interval. And similarly you can find the area of this rectangle. So this height is the maximum of f on this interval, which is m sub 1, capital M sub 2, sorry, capital M sub 2. If you multiply that number by the width of this interval, is that gives you the area of this rectangle. If you sum these rectangles up, so you get so we denote that one, that one is big Q of this partition and this function. So this is the upper sum, this we call, so we call this is the upper sum of f, corresponding to the partition P, right? So you get to add these areas, right? You add them up, you get the upper sum of this part, upper sum of f corresponding to the partition P. So this is the definition, right? This is the upper sum of f corresponding to the partition P, right? That means the sum of these areas. It is clear that the sum of these areas is bigger than the integral of, so the curve, the area under this curve, right? So the sum, upper sum denoted by capital U, upper sum of, upper sum of f corresponding to partition P. So which is sum, we split into n sub intervals, right? This sum goes from 1 to n. So m sub I times xi minus xi minus 1. So this is the upper sum of f corresponding to, right? So this number, that number gives you this, the sum of areas of these rectangles. That number is bigger than the area of this curve. So area under this curve over this interval AB. So this number is less than or equal to, let's denote that, integral of f over a to b. Let's denote that one. The area under the curve over AB interval is denoted by this one, integral of f over AB interval. This this value is less than or equal to upper sum of f corresponding to this partition P, any partition P, right? Similarly, you can define the lower sums here. So lower sums of f corresponding to P partition is denoted by this, right? This simple m sub I is the minimum of f over minimum of m on this interval, this sub interval, right? Times the width of that sub interval, which is denoted by delta xi, right? If you add these things up, right, so you get the lower sums. Let's try to understand this one using the previous diagram. Alright, so here I use blue pen to denote lower sum, right, of f, right? So in this, if you consider this sub interval here, the minimum value of f on this interval is somewhere here, right? Let's complete a rectangle. So something like this. Alright, yeah. Let's complete a rectangle. Okay. And if you consider the next sub interval, which is x sub 1 and x sub 2, this sub interval, the minimum value of f somewhere here, and I complete a rectangle. And here as well, I keep doing this. So you can notice that you can notice final one. Not previous. I have another one to color. Alright. Alright. So if you consider the sum of these lower sums, the sum of these areas of blue color rectangles is denoted by capital L, lower sum of f corresponding to the partition P, right? So what you can notice here is the area of this curve, over AB interval is bigger than the sum of lower sum, right? The area of this curve over this interval is bigger than the lower sum. Lower sum is sum of areas of these blue color rectangles, right? So the area of that curve over AB interval is bigger than this lower sum of f corresponding to P partition. which is the sum goes from 1 to n. We split n subintervals, that's why. So this sum goes from 1 to n, right? And so this simple m sub I, this means the minimum value of f on this subinterval, on this subinterval x I minus 1 x I subinterval, right, times the width of this subinterval, width of that one x sub I minus x sub I minus. So the thing is, lower sum is smaller than, less than or equal to the area under the curve over AB interval, and we can say that this area over AB interval is smaller than the upper sums of f corresponding to this partition. So this remark is completely correct, clear, right? So for each partition P of AB interval, right, lower sum of f corresponding to that partition is smaller than the upper sum of f. This one is very clear, right? So, and what we notice here is, we said that the lower sum is bigger than, so let's read this theorem here. Suppose that f is continuous on this interval AB, right? Then there exists a unique number I that satisfies this inequality here for each partition of AB, right? We show, so from this picture here, so from this picture here, this red is denoted by uppers, and blue colors the sum of areas of blue color rectangle is the lower sum, right? So it is clear that from this picture there exists a number. You can prove that one. So you can get an intuition here, right? So the lower sum and upper sum, there exists a number in between lower sum and upper sum, right? So right. So last week I did a video on integrals, first video, right? So I showed that if you add a point, what happened to lower sum and upper sum? If you add points, what happened to upper sum? Upper sum is decreasing while the lower sum is increasing. Alright, let's look at this theorem here. Suppose that f is continuous function on this closed interval AB, and suppose P and Q are partitions of AB, two partitions, right, of AB, with P is a subset of Q's. Q is the bigger set, so Q has many subintervals than P, right? P is a subset of Q, so that means there are many points. There are a lot of here Q has extra points, right? So this partition has extra points. That means so that means what happened to upper sum? So upper sum is decreasing. The upper sum of f corresponding to q is smaller than the upper sum of f corresponding to p partition. And what happened to lower sum? Lower sum is increasing if you add points. So lower sum of f corresponding to p is smaller than the lower sum of f corresponding to q, right? Right, you understood this one very clearly using the my previous video, right? So I'm not going to prove these theorems. You have to understand these things. We don't prove these theorems here, right? But I will upload some lecture notes to understand the proof of these theorems, right? Look at this definition here. Look at this definition, right? Suppose f is a continuous function on this closed interval AB, then the unique number I that satisfies the inequality. So it is clear that that unique number is this one. We understood from this picture, right? So upper sum and lower, so there exists a number in between upper sum and lower sum of f corresponding to this partition, right? Which is very clear now. So in my next video, I'm gonna solve some problems regarding using these definitions and theorems, right? So I hope you understood what we did today, right? So if you have any doubts, you can reach me. You can write an email, or you can use LMS forum, anything, right? All right, good luck.